In this video, we're going to introduce cylinders and quadric surfaces. So, back when you've studied graphing in 2 dimensions, you've certainly investigated graphs of equations that have only one variable in them, like x equals 1, like y equals -1 or x equals 3. And these turn out to be either, in the first case, a horizontal line, in the second case, a vertical line, and the reason's pretty easy. The missing variable means that it doesn't matter what that value is, it's not going to affect whether or not the equation is true. So for example, if we look at the equation y equals 1, for point xy to be on that graph, the only thing that we require is that the second coordinate, the y coordinate, has to be a 1. The x coordinate can be whatever, and you satisfy the equation y equals 1. So the x coordinate can be absolutely anything, and the y coordinate is equal to 1. That means we're going to be able to draw that horizontal line. In 3 dimensions, of course, it's a little bit more interesting, but the same exact principle applies. If one of the variables is missing, then that, or more of those variables is missing, doesn't matter. The value for that variable can be whatever you want it to be. Doesn't matter what it is. And we call these types of graphs cylinders when we have one or two of the variables missing. Those are referred to as cylinders. The surfaces that we'll get are called cylinders. So let's see if we can do a couple of sketches of these things. Let's say we want to sketch the graph of x squared plus z squared equals 4. Well, let's first consider, okay, the y is missing, so let's just consider what happens in the xz plane. Well, I think we can pretty readily recognize that this is an equation of a circle. It would be centered at the origin, and it would have a radius of 2. So here is our three-dimensional coordinate axes here. Here's the x-axis. Here's the z-axis. So the red axis is the x-axis. The blue axis is the z-axis. And we've drawn the circle of radius 2 in the xz plane. Now, the y variable is missing. So that means the y coordinate can be any value as long as the x squared plus z squared is equal to 4. So we can extend this circle infinitely parallel to the y-axis. So we can think about lines coming out of that circle and just being parallel to the y-axis. And for any point on that circle, we can do that. So if I imagine that here, I get what looks like a traditional circle. It would be infinitely long, of course, but again, we would imagine just taking a point on the circle, extending it infinitely in both directions as a line, and keep doing that for every point on the circle. We end up with this cylinder. Let's look at another example. Let's say you were asked to sketch the graph of y equals z squared. Well, we'll approach this the same way. Let's first consider what happens in the yz plane. Well, that's a parabola, and it opens in the positive y direction. So it's like y equals x squared, except that we replaced it with a z. So here's the y-axis, and again, here's the z-axis. We're going to have this parabola that opens in the positive y direction. So we've got the sideways parabola with the y-axis running right through its middle. And then just like the previous example, the x is missing, so we would run infinitely in the x direction along lines that are passing through that parabola perpendicularly, if you will. And we get this parabolic cylinder in this case. That's what we refer to this. Imagine it's a sheet of paper that's been bent, essentially, is what this looks like. All right, so those are cylinders. Let's think about what we refer to as quadric surfaces. So in that previous example, we thought of that y equals z squared in the yz plane. That was a parabola. That comes about from a quadratic equation. So did the x squared plus z squared equals 4 came about from a quadratic equation. So we're going to come across those in this particular case with quadric surfaces. Again, thinking about it in terms of 3 dimensions, having a quadratic terms in 3 dimensions. So the graphs of these types of equations will end up being surfaces, and the general second degree equation, this is why we call them quadric surfaces, because they come about from a graph of a general second degree equation,
Looks like this form. It's a big, long form. we won't deal with a few of these terms at all. That's the x squared, the y squared, and the z squared are the ones that we see these quadratic terms, these second-degree terms. These three here are also second-degree terms where we've multiplied variables together. So you can do an x times a y times a z, an x times a z. We would not have an x times a y times a z. That's a third-degree term. So the mixed second-degree terms can only have two variables in them. And then we could also have linear terms here in each variable, because that doesn't get our degree any higher. And then, of course, a constant term here is what that j is representing. Generally speaking, these xy, yz, and xz are rotation terms. They spin things off the axes, if you will. And we won't be dealing with those. So the problems that we come across will not have xy, yz, or xz terms in them. And generally speaking, also, the linear terms are translational terms, meaning these are going to shift things left, right, up, down, front, back. So after appropriate rotations and translations, basically we can boil all of our quadric surfaces down to two cases. We can do the ax squared plus by squared plus cz squared plus j equals 0, or ax squared plus by squared plus iz plus j is 0. So we can boil it down to the square of each of these, the variables times some constants, or the square of two of them and a linear one, and then again times some constants. So let's see if we can investigate all of these cases, or at least a few of these cases. Let's first look at the graph of the equation x squared over 9 plus y squared plus z squared over 16 equals 1. What we're going to do to help us graph this type of an equation is consider what we refer to as traces. And what a trace is the intersection of the surface with each of the coordinate planes. Well, a trace is with one of the coordinate planes. So we're going to look at the xy trace, the intersection with the xy plane, the xz trace, and the yz trace. Those will be the three that we're interested in. So, to find the xy trace, well, we were looking with the intersection with the xy plane. Any point in the xy plane has a z coordinate of 0. So what we're going to do is we're going to plug in 0 for z, and we will look at the resulting equation and see what kind of graph we have. Well, the resulting equation in this case is x squared over 9 plus y squared equals 1. We recognize this is the equation of an ellipse. The 9 in the denominator tells us that we go left and right 3 units from the center. I guess I should say out and back, since I'm talking about the x-axis here. We would go out and back 3 units from the center, and this is centered at the origin because we have not subtracted anything off the x or the y. There's an understood 1 in the denominator here for the y squared, so that means we would go left or right along the along the y-axis, 1 unit on either side. So this is what's telling us where it crosses the x-axis and crosses the y-axis. So we get an ellipse in the xy plane. Similarly, if we do the xz trace, we'll set y equal to 0. We get another ellipse. In this case, we still cross the x-axis at plus or minus 3, but now we cross the z-axis at plus or minus 4. Finally, if we do the yz trace, setting x equal to 0, we get another ellipse that crosses the y-axis at plus or minus 1 and the z-axis at plus or minus 4. So let's see if we can get these traces in here. So here, this one here, looks flat. This is our xy trace. Notice it crosses the x-axis at 3 and negative 3, and the y-axis at 1 and negative 1. This one that's elongated this way is our xz trace, crossing the x-axis at negative 3 and 3, and the z-axis at negative 4 and 4. And then finally, this one that looks up and down but is skinnier than the other one. This is our yz trace. It's crossing the y-axis at negative 1 and 1, and the z-axis at negative 4 and 4. any other trace we try to do that's parallel to one of the coordinate axes, so say something like maybe x equal to 1 or y equal to 3, anything parallel to one of the coordinate axes that intersects this surface will also be an ellipse. So we get what's referred to as an ellipsoid, and these traces help us get a little bit better idea of what's going on, and that would be our graph of the surface in this case. And you can see the traces in there. I kept those in there, but shaded in the rest of them. So we get this, well, again, we refer to it as an ellipsoid. Kind of maybe a, not pointed, but kind of a football type of shaped thing. An egg-shaped thing. Let's look at another quadric surface. Let's look at the graph of y equals x squared plus 4z squared. Again, let's look at traces. The xy trace is a parabola. Putting z equal for 0, we get y equals x squared, so we get a parabola. That one was pretty straightforward. The yz trace is also a parabola. It's a little skinnier parabola since we have 4z squared rather than just z squared. But we got a couple of parabolas. The xz trace in this case, though, if we plug in 0 for y, isn't exceptionally helpful because we get the equation x squared plus 4z squared equals 0, and the only point that satisfies that equation is the point 0, 0. It's the origin. So what we're going to do in this case is look at traces that are at this intersection of the surface with planes of the form y equals k, changing that number from 0 to some other number just to see what the traces look like. Well, if we replace the y with values of k, provided that the k is actually positive, we get ellipses again. So every trace that is parallel to the xz plane, every trace that along the plane y equals k is going to be an ellipse. So let's see if we do a graph of some of the traces here. All right, so this parabola here, this one at the bottom, going around and going up to the top, that was our y equals 4z squared. This one here, that's flat and then is dashed in the back, that was the y equals x squared. And then we've got the ellipses that are the traces that are formed by planes that are parallel to our xz plane. So as we cut it vertically, perpendicularly to the y-axis, we get ellipses for our traces. So we get a surface that's referred to as an elliptic paraboloid. Elliptic because of these elliptical traces, and then paraboloid, of course, because of the parabola shape. It looks like a bowl. And if I shade, this is what the graph looks like. All right. So here are some general forms of the different quadric surfaces you might run across and what a representative graph would look like. An ellipsoid we've seen looks like this form. Again, we're not doing any rotations at all, so those products of variable terms wouldn't pop up, but we might do translations. It's possible we could shift this out, back, left, right, or up or down. Much like what you do for circles and centers, you could just subtract values on the inside of each of these squaring, and that will shift the center of the ellipsoid appropriately. We also get what's called an elliptic cone. Sometimes you'll hear it called a double elliptic cone because we got one that's on the top and one that's on the bottom. In this case, we've got the z squared over c squared on one side, and the x squared plus y squared over appropriate constants, what have you, on the right-hand side. If you flip these variables around, you would still get cones. They would just go along different axes. So what I mean by that is, if this were an x and this were a z, this would still be a cone, except that the cone would be going along the x-axis. The x-axis would be running through the middle of the cone, as opposed to the z-axis. Elliptic paraboloid we saw on that previous one. We had y equals x squared plus 4z squared, but we still had that paraboloid idea. This one's written as z equals x squared over a squared plus y squared over b squared. Again, the important part is that we've got a variable, the first power on one side, and the others are squared and added together on the other side. Hyperboloid of one sheet. You get hyperboloids when you've got each of the variables are squared, two of them are positive and one's negative when you put them all on one side. Then you get a hyperbolic paraboloid if you've got a z on one side, or a variable in the first power on one side, and then the difference of the squares of the variables on the other side. We get where it looks like a saddle in this case. And the black graphs here are representing traces of what these things look like. And the last one is a hyperboloid of two sheets. Hyperboloid of two sheets comes about when you have all your variables are squared again, but two of them are negative and one is positive. When we're graphing these things, we want to try to recognize their forms and be able to use their traces to help us get a little better shape of what's going on.